Rest.
So what exactly is radioactivity? Read quick, read quick. Well, it's what measures radioactivity? What machine? No, what machine? Geiger counter. What it does, it counts the number of the nuclei that are being released. Because what's happening in the element itself is getting super excited. It's unstable. It doesn't stay contained, which means some of those molecules, the nuclei molecules, are being escaped, and they escape at very high velocity. And that's where the radioactive heat comes from. So if you ever see, I mean, literally radioactivity can melt metal. And it just rots the body from the inside out. What happens, it goes to the cellular level, it goes from one nuclei to another nuclei and starts eating away at that and just burns you up from the inside. It's a very harsh thing. And imagine Madame Curie, who didn't know all this, but she discovered it, and she was always researching and getting more and more and more. But she had to do it because if it wasn't people like her, we wouldn't have MRI machines or death rays.
It's pretty neat how much you do. Like between her time.
Oh, if there's a movie about how she did it. Her and her husband went and got a whole bunch of dirt. It says they got, let's say 47 truckloads, 100 truckloads. And out of the 100 truckloads, maybe a cup of that dirt is useful to get the radioactivity. And then out of that cup of dirt, maybe 3 elements are radioactive. So imagine, see how much stuff you need to break it down, break it down. And it's a whole lengthy process. She and her husband were stuck in this makeshift lab that they created, that the windows are broken, it's winter time and raining. And they were just trying to do all this stuff because she had an idea. She knew it was in there and she had to find it. Excellent story. And then afterwards, they still wouldn't allow her to be in the Royal Society of Scientists and Engineers. So, or teach at the university until finally they said, yeah, okay, we'll let you do it. So, radioactivity is the unstable atom spontaneously emitting mass, or actually that should be equals. That's what radiation is. So it's letting go of some physical part of it. The rate that the radioactive elements decay is roughly proportional to the number of nuclei remaining in the element that you have. So the number of nuclei that change per unit time. That's what we're looking at for radioactivity. And that's what you hear on that Geiger counter. Every time it goes click, 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 those are one of those super excited elements, nuclei particles that come and are detected. So it's pretty cool. And what we're doing here now, because we're looking at the number of nuclei with respect to unit time, K is the constant value, and it's positive. Why is it a negative KY? What's that? It's decay. Elements are being lost, so it's decreasing. And what happens is as more and more of these nuclei elements leave, the element becomes more and more unstable. And what happens then? Once it becomes unstable and it loses enough electrons or nuclei particles, it becomes another element. It goes down on the periodic table to a lower element that's also unstable. And it keeps on losing until it goes to another one. And it keeps on going down.
Radioactive.
It becomes, yeah, it won't ever become something non-radioactive. It's always going to be radioactive because it's losing particles. It's very unstable. Now, when it gets to a certain point, will it explode because it becomes unstable? That's right. Is a millisecond, right? What is half-life? Right. It's how the time it takes for the element to have decayed by a half. So there's the number of nuclei in the molecule itself to lose half of their elements. Because once it loses all of them, then it's no longer it. It's now at the next lower stage. There's not, I don't know if you took chemistry, you know, you have the orbitals, the electron orbitals. As it loses electrons, it now becomes further and further unstable, and it changes it changes elements itself. So it's pretty cool. So let's see here. Do we have an example? No, actually, that's the wrong page. There is. Have to no examples yet. No examples. So example 5, there it is. Example 5 says this. Oh, let's read it. The decay of radioactive elements can sometimes be used to date events from the Earth's past. In a living organism, the ratio of radioactive carbon decay, carbon-14, to an ordinary carbon stays fairly constant during its lifetime of the organism, being approximately equal to the ratio of the organism's atmosphere at the time. After the organism's death, however, no new carbon is ingested, and the proportions of carbon-14 in the organism remains decreased as the carbon-14 decays. You ever hear of carbon-14 dating? That's what they're looking at. They know what they have. They're going to see how it decayed from however long it is. And they're going to work backwards to come up with the time. Scientists who do carbon-14 dating often use a figure 5730 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present has decayed. So the bottom line. They use a figure of 5,730 years for its half-life. Find the age of the sample in which 10% of the radioactive nuclei originally present have decayed. So let's put this into math terms. All right, so with what we have here, what do? How do we solve this? It's okay, let me put down what it said. Okay. Use 5730 for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. So we'll use that formula. That's the half-life formula. So what do we put in there? What do we have to find? We have to find K. Why do we have to find K? Well, we need to know it because remember, all the other formulas we had are always e to the power kt. So we have to have the constant to help us find the time in which it existed. So what do we know in this equation? What's that? We know the half-life. H is what? So plug in what we have. So now what do we do? Now we solve for so we have K is equal to ln2 over 5730. So on top we have ln divided by it equals 1.21 times 10 to the negative 4. Mhm. Where is that? So we have our K value. Let's use our function. Initial e to the negative kt is equal to y, and y represents the number of molecules, nuclei we have left. So there. We know K is 1.2 times 10 to the negative 4. What else do we know? What's that? We have to find T. How long? Do we know what Y equals? This whole thing here. How much is left? The question said, find the age of the sample in which 90% of the radioactive nuclei originally present has decayed. So we know that this has got to be 90% of the original sample. So if that's the case, then E negative KT equals 90%. Because think about it, it's 90% of the original sample. The original sample's here, so therefore that has to be true. So we got to find T from this equation. How do we do that? Well, first thing we got to do, we got to change 90% into what? .9. It has to be decimals. How do we get the T down? ln. Take the ln of both sides. The ln and the e cancel, so we have negative kt equals ln 0.9. Does that negative sign matter? Why? Is it always going to be there? Because what is ln 0.9 going to be? It's going to be negative, because remember, anything less than 1, it's negative. So the negatives are going to wash out, which is what we're looking for, hoping for, because we can't have a negative time. Let's see what we have here. We know, well, we know that k is equal to the ln to 57, was 5730. So we could put that in there. Well, change the signs. How do we get t by itself? Multiply by the reciprocal. So those cancel, those cancel. So t is equal to negative ln 0.9 times 5730 over ln2. Let's see what this equals. I'm sorry, let me get cut up. So let's see what these numbers give us. So times clear entry. We got open parenthesis 0.9 ln close parenthesis times open parenthesis 5730 divided by ln2. It's a t equals positive 870.977, which is approximately 871 years. So far, so good. It's you find the relationship of what you're looking for and what you have. Okay. Next, we'll talk about Newton's law of cooling. More so heat transfer. Can you guess what it says? With what we know so far of the real world, what do you think the law of cooling is? Or if you have something that's hot, what is it? What is the process to make it cool back down to room temperature? It's proportional to what? Time is one thing, yes, but it's more proportional to the atmosphere around it. It starts, if you had a red hot plate or a pan and you put it in ice cold water, the gradient is a lot bigger. So with what would happen to the cooling effect there? You'd be surprised actually. Is it faster or slower than if it wasn't red hot? It would be the hotter it is, the longer it takes to cool. Because think about what happens when you put the red hot pan in the water. It starts bubbling, right? What that means is around the pot, there is a very thin layer of air, the bubbling that happens. So there's very little heat transfer really happening. It's now that's immediate physical reaction, and it takes longer for the reaction to happen. What's that? You got your hand up?
Oh,
Right. So let's look at what we have for. So it's proportional to the heat of the object minus the heat of the object minus the heat of the surrounding. That is the basic rule of any type of heat transfer. It works both ways. If the heat of the object is higher than the heat of the surrounding environment, or if it's lower than the heat of surrounding, it's either cooling or it's heating. In other words, if you had a pan that was frozen in the freezer for 2 weeks and you put it in room temperature water, what's going to happen? It's going to bubble again, actually, and then it's going to warm up. So what we're looking at here, so this is the basic change. Right. But that's exactly what's happening is because as the water molecule hits it, it instantaneously heats up and it has a layer of water, bubbling water between the water and the pan, which is how you can tell when you have a super hot pan, you put up some water and it just glides around. And it doesn't get smaller instantly. It takes a long while for it because it doesn't spend that much time in the pan. It's always jumping. Same way skis work. If you ski on a mountain on snow, what's happening is the ski on top of the snow because of the friction melts that snow, and you have a layer of water that you're skiing on. And as soon as you pass by, it's so thin that it refreezes instantly behind you. Ice skating is the same thing. The blade on the ice never really touches the ice. It touches the water that's between there. That's why you slide so fast. And then, but if you offset it and you let the water go out, then you have the ice against the steel. But anyway, so similar to what we had originally. Let's see, where is that? Yeah, it was dy dt is equal to negative ky. And the y is the initial kt. So this is the concept that we'll be staying with. If you notice, we have the same thing. We have the negative k times the y. The y is the difference in temperatures. So let's say this equals our y. So if we take the derivative of this, what happens? With respect to time, so you have the derivative of negative k h0 hs over dt. Negative k is a constant, so it goes out in front. Now what we do? How can we solve this? Well, we could distribute. We could do, here's our negative k. We take dho over dt minus dhs over dt. Again, what does HO represent? The heat of the object. HS is the heat of the surrounding area, the surface, whatever. So, are either of these constant? The heating of the surrounding, the room temperature is constant. So that, when we take derivative, goes to 0. So we have the derivative of HO over dt. The derivative of HO, we'll just call it H. What is dH dt? Have we seen dH dt before? It's right here. The change of the temperature, heat, is the difference between the object and the surrounding area. So we can write that as negative k h sub 0 minus h sub s. And we know that this is equal to y, the difference. So that's what we're looking at. We're looking at, this proves that the function itself works. And what we have to do now, let's look at an example. Actually, we have to have this somewhere. So where does that E negative KT, what do you think it would go to? Let's see. So we know that H is HO minus HS. What we want, we want the effects of this to experience the decay. The decay in this place is what? It's the heat loss or heat gain. It's exactly the same as radioactivity. Think about it. Radioactivity is the nuclei leaving and going out. What do you think heat is? Heat are the heat molecules, that excited molecules that escape the object itself and makes it more and more and more sturdy and steady. So let's look at example 6. Example 6 says this. A hard-boiled egg at 98 degrees Celsius is put in a sink of 18 degrees Celsius water. After 5 minutes, the egg's temperature is 38 degrees Celsius. Assuming the water has not warmed appreciably, how much longer will it take the egg to reach 20 degrees Celsius? So there's everything we have. A hard-boiled egg at 98 degrees Celsius is put in a sink of 18 degrees water. After 5 minutes, the egg's temp is about 38 degrees Celsius. Assuming the water has not warmed appreciably, how much longer will it take for the egg to reach 20 degrees? So what is HO? What is HS? Yes. What's HS? So what do we do with that? So here we have the formula we'll be using. So we have H equals HO minus HS E negative KT. So what do we do here? Let's fill in the blanks. What's the question asking? Well, we have to first find K, correct? How do we do that? One more time?
Like use that.
So we have the time, yeah, so what do we have here? We have time equals 5. HO equals 98. HS equals 18. What else we have? And we're looking for H equals 20. The final, how long will it take for the egg to reach 20? So what is it? What's the equation we'll be using here? Because this is the heat, the temperature, the heat of what? What does this represent? That's the heat of the egg, isn't it? So now when we put the egg in the water, we have two different temperatures we're putting in there. So we have the heat of the egg plus the heat of the water. So the overall heat is the heat of the water plus the heat of the egg. The heat of the water is 18, and the heat of the egg is HO minus HS e to the negative KT. So 18, what's HO? 98. H of the surrounding, which is the water, which is 18. E negative, what's time? Where does this come in? That's the H after 5 minutes. So the only variable we have left is what? K. So we have 38 minus 18. 98 plus 18 is 80. Subtract 18. This is the last example. So what do I do next? Get rid of the 80. How? Divide. So the zeros are gone. We get 1/4. How do we get the K off the exponent? Ln to both sides. So the ln of 0.25, so I'm gonna ask space. These cancel, so we have negative 5K. Change the signs, we have negative ln 0.5, 0.25, I mean. And divide by 5. So we have 1/4 equals e to the negative 5k. Take the ln of both sides. So the ln of 0.25 is equal to negative 5k. Change the signs. 5k equals negative ln 0.25. 0.27725. So now what do I do with that? Have we answered the question yet? It's asking us for how long? So our formula we have is negative KT. Negative 0.27725 T equals what? What was the original part? Equals 20. Repeat the process, solve for T. Divide by 80. So it's 1/40. Take the ln of both sides. Now, do we have to write this all the time? 1/40? Is there, if we expand it, what happens? Remember, if it's a fraction inside here, what happens? That becomes ln A minus ln B. So we have ln 1 minus ln 40. ln1 is 0. So we have negative ln40, they're both negative, so we get rid of the negatives. So now we have ln40 equals 0.27725t. So t is equal to ln40 divided by 0.27725. So let's see what happens. ln40 divided by 0.27725. So time equals 13.31. So what units are we going to use there for our time? Minutes. So it'll take about 13 minutes before it goes down to 20 degrees. If you think about it, what's really cool about this is you can now determine exactly how long it'll take you to cook a dinner or make breakfast. You know exactly to the second how many minutes it'll take.
The amount of time it took to do this, yeah.